Oh, that's so much nicer.
I guess we can start now. I think we have two participants with us. We can start. Hello, everyone. Good evening and good morning. Uh, my name is Vani, and I'm the head of Department of Aerospace at Hex-Star Universe, and I'm going to be host of the day today for this session. And first of all, thank you everyone who has joined here with us today. Today is the sixth day of World Space Week celebration, and the topic we are going to discuss today is exoplanet and life beyond Earth. And today, to enlighten on this topic, we have none other than Mr. Trevino. He is an aerospace scientist, an astrobiologist, and also the co-founder of Space for All and Magnetospace. We're honored to have him here with us today. A very warm welcome to you, Mr. Terry. Over to you.
Vani, how are you? Where are you in India?
I'm good. Right now, I am in Chandigarh, which is the capital of Punjab and Haryana in India.
A good friend of mine is from your neck of the woods, Tarun. Tarun is at University of North Dakota. He's a master's student there. You probably know him. He knows everyone. Anyway, well, I'm happy to get started. We can, if I'm able to share screen, I'm ready to rock and roll. Excuse me. Here we are. This is a quick kind of an overview of what I've been working on for the past several years. I did just finish a workshop in July at Caltech, and we were working specifically on understanding how we can use data to help us locate exoplanets. Excuse me. This is a brilliant image. So real quickly, first of all, who I am. Yes, aerospace scientist. Yes, I'm an exoplanet hunter. I enjoy what I do every day. I get up every day excited about the opportunity to tell people on this planet what I do. And the number one reason why is because we are out there looking for life beyond our world, perhaps maybe understanding eventually what it is in our world here on Earth that created that life. You know, there's a big argument existentially about that, and I'd rather not get into that conversation, but we can if people want to. This image is from the Gaia data, but by the way, a lot of this conversation, I did kind of edit a little what I'm going to chat about today. Can't find an exoplanet until you find a star that has an exoplanet. So Gaia is a brilliant source for that, and I'm going to use a lot of the information that I received from that meeting. It was enlightening to know that this telescope, which is up in orbit at L2, other side of the moon, and is doing an all-sky survey 24 hours a day for us. We're getting so much data. It's actually being dumped down to us in tranches. This most recent data was DR3. DR3 was was enlightening more than any other, maybe other than James Webb Space Telescope recently, and probably the most awesome bit of data that I've seen in a great number of years. DR2 I thought was spectacular. This is exponentially greater. This image is, these are star trails. And these are the estimates of stars that we know that we've actually, we've gone out and we've surveyed with Gaia. And then we've estimated the track of these stars over the next 500,000 years. And so if you follow every one of these lines, if you could grab this and zoom in and you follow every one of these lines, it's where that star is in the parallax that we've measured accurately, more than accurately, probably to within the arc second, and then extrapolated that out to 500,000 years and followed that exact measurement. And the reason we can do that is we've taken, if not dozens of measurements of these stars, we've taken sometimes more than that. Sometimes we've taken 70, 80 measurements of these individual stars. And now we're at 1.8 billion. That's 1.8 billion with a B number of stars that we've actually cataloged. So Gaia is really so it's an astrometrical telescope. We use astrometry as a means of determining location, trying to find exactly where something is. Parallax is the number one means of doing that. These are all visually accurate as well. And so what I wanted to do is I wanted to start with how we find these exoplanets. So many of you have probably heard all of these methodologies. You could just get lucky and run into one, and that's timing. You could get dynamic, right? And that's on the dynamic side. So you can use radial velocity, astrometry. You can go out and maybe get lucky and get a microlensing event, which some are predictable. And we can use those to perhaps see, and in many respects, microlensing is just an amplification of something that might be around a star. It's certainly not accurate in terms of parallax, but it gives us a really good visual identification of what may be around a star. We can do direct imaging. There's only one that we know of for sure, 100%. I'll share that in the very last slide. And by the way, I'll share all these slides with the team after the fact. And I'm going to credit this slide to Dr. Perryman. Dr. Perryman is kind of the founder of Gaia. He came up with the idea of using the all-sky telescope as a means of tracking stars. And then he also wrote a brilliant book. It's called Exoplanet Handbook. If anybody wants to read it, I've met him. I've had lunch and dinner with him and breakfast, and he's brilliant. He's out of the UK, so you may run into him occasionally, perhaps. Photometry is probably the best means that we have of locating these exoplanets. We're not going to do, without knowing the host star and knowing about the host star, there's no way that we're going to run into a rogue planet like that we may with James Webb Space Telescope, but very unlikely. It has happened, and it will, and we'll probably have those reports, but they'll be one-offs. They'll be there'll be one in a zillion. And in this case, the best means of us finding something is going to be through photometry, my opinion. You might get lucky and you might see something, you might see a curve in a protoplanetary disk, which also fascinates me. And I've done a deep dive into protoplanetary disks lately, understanding what those perturbations are that you see when you look at an Atacama Desert telescope from maybe, what's the all-sky telescope there in the Atacama Desert? I forget the name of it. Yeah, so if you get a chance and look at some of that data, and it's just fascinating to see planets form, planets in their moons even. I started looking at the magnetospheres of these stars and understanding, what is it in these stars that kind of enable the formation of planets. there's definitely some type of magnetic event. Doesn't get spoken about a lot, but those create perturbations in those interstellar medium. And if you get an ISM that gets a little blip or a little bump in that interstellar medium, and that all of a sudden you might have just enough perturbation to kick off angular momentum, and before you know it, you've got a planet forming. Now, granted, it takes 1 million years to form a planet approximately, and that number is probably not real accurate, but in astrometrical terms, it's probably not far off. This is a brilliant slide. So the last thing that I wanted to really show everyone on this slide is up in the upper left-hand corner here. This was as of January. We had 4,911 confirmed exoplanets. We had 3,676 systems, and then we had 812 multiple systems, meaning multiple exoplanets. That's in January. Now I think we're at 5,000 and change. We might be at 5,100 or certainly quite close. But just so you know, there are lots of planets out there. And again, I'm going to, everybody will have access to these slides. We'll be able to share those at the end of the presentation. I'll send them out. Without knowing where the stars are, we are not going to be able to find the planets. This is really a composition. It's an artist's impression with accurate measurements of stars as they're moving through our Milky Way. Got to tilt yourself a little. You got to look at it and go, why is it, what's going on here? Most of you know we had a collision with another galaxy a couple 100 million years ago, approximately. And this is the result of that collision. And you can even see the stars as they're moving up and through our Milky Way and leaving, and they're not coming back wherever they're heading. So I just was fascinated with this image. And it was Koppelman who came up with it, Koppelman, Villalobos, and Helmy, and they did the simulation. It's a computational simulation, but it's brilliant. It's eye-opening to know that even as we sit here in today, we've got stars that are never going to come back, right? They're leaving us, and they're leaving rapidly, 200, 300 kilometers per second. I just wanted to share this. This is a brilliant image. Gaia really has, since DR1, now DR3, where we're at, has changed everything. And I'm assuming James Webb Space Telescope is going to do the same. And again, I have a couple of slides at the end that are definitely proving that. We're getting astrometric data. It's real time. We're at 1.81 billion stars. Billion. I always just can't fathom that number sometimes. We're seeing these stars in their relative motion. We're seeing and getting real-time RV data. So radial velocity, as everyone knows here, tells us as a star is wobbling and as the motion of that star is spinning towards us on its axis, we're getting either a red shift or a blue shift away, or blue away, red at, blue away. Spectroscopy at a really high level. The spectroscopy is interesting. They're only using red and blue to kind of discover what's going on. And so we're not getting a bunch of confirmations using spectroscopy, but it's quite a bit. It's in the thousands. They're also mapping our interstellar medium, and you're also going to get wandering rogue planets and asteroids. The photometer on this thing is a really low resolution, but because it's low resolution, we're seeing movement, which is just mind-boggling. This is I love this image. So these are actual stars that have been mapped and where they are in the middle top here. You really can't see it because I didn't get a really high resolution image of that, unfortunately. But you can go to Western Washington University and grab that image in its higher resolution. Caltech, Professor Hurt came up with this kind of estimate of what our Milky Way looks like. I think that's pretty fascinating, and also to think that we're down in this lower Sagittarius arm. This also kind of speaks to this middle bottom, speaks to that collision that we had, and these are the stars that are perhaps exiting. Some of them might be coming back around. As you can kind of see, we're getting relative motions that are showing that we are getting angular momentum. And real quick, just an aside, angular momentum, stars, big galaxies, and we're not a big galaxy, by the way, at 1.8 billion stars so far. It always makes me think, with that big black hole, Sag A in the middle, maybe there's something else going on. Perhaps it's the combination of all these stars as their motion's taking place and as they're getting gobbled up by our black hole eventually, perhaps. Where does all that data go? Where does all that information go? Sorry, just an aside. Taking a look at an HR diagram, most of you probably know about the Hirschsprung-Russell diagram, I'm guessing. Brilliant for us to kind of understand where we are in the main sequence. You can kind of see the sun is being mapped right here in that we want to call it the Goldilocks zone for the sun itself. And, these are really high mass, right? So they burn out really fast. These are probably only going to be stars that live for 10 million to 100 million years. And then you've got the 10 billion year old stars down at the bottom. I love these offshoots where you can kind of see the super giants and then the red giants, and they're all coming around. White dwarfs lately have been fascinating me, and we can talk about that after the fact. There's a reason for that, because they're cool and somewhat stable, and perhaps there's quite a few planets in orbit around those. Because we're over 1 billion right now in terms of the number of astrometrical readings, spectrophotometry, that's a mouthful. If you can say that 3 times fast, hop on and say it for fast. No, I'm kidding. RV for 100 million plus objects. The survey is down to G equals 20V, V equals 20 to 22. It's nice that they're kind of in balance. And that tells me that because of the forces that are out there, it tells me that we're actually seeing just about everything. Gaia is going to tell us a lot about what's going on our planet eventually, but that's going to be our jobs as exoplanet hunters. And we've got our work cut out for us. Launched in December 2013. If anybody knows it, it's L2. I think I mentioned that earlier. Estimated now to have its end of life in 2025. It might get extended a little more. They're running into some problems with the microthrusters. The microthrusters are going to run out of fuel. That's keeping it quite stable, so we don't get any of those weird aberrations that you might get. And we shall see how it goes. Stars themselves, what we found, and the reason I'm talking about stars, we can't find exoplanets without stars. Rogue planet occasionally, but the reason I wanted to visit with you today about Gaia particularly is these are kind of what we've found. We've got variable stars. We've got low resolution spectroscopy on about 470 million stars approximately. Spectra on about 220 million of them, of the total of 1.8 billion. Astrometry, photometry at 1.5 billion at the bottom down here. As we're getting into that higher resolution spectroscopy, good news is we've got, probably 1 million stars that we can go out and look at closely, and perhaps even determine, if there are exoplanets. This tool is going to help us narrow down what to look for and where to look. And that was the point I wanted to bring Gaia up. So here's the release in general. Again, this is a lot of data, so I'm going to just let you you all have an access to it. Everything's on the Gaia website if you want to go and join. It's free. All the data is there. No reason for you not to go through those methodologies, so that you can actually do the work. Which is endlessly fascinating. Some of the things I liked and I wanted to highlight here. So we're looking at RV data at about 333 million stars. That's a pretty spectacular number. If you wanted to go really into and try to think, well, what are we finding? We've got solar system objects for us alone in our local market, you want to call it. We've got 23 million objects as we found just here in our little solar system. That gives you an idea how much mass is out there. This is just, if you wanted to really dig into this, microlensing events, look how few microlensing events there are. And then how many transits. They're not seeing a lot of transits, which is interesting. And I'll mention this here in a minute, the reason why. Because it's because of how we're oriented to the other stars. But this is a brilliant thing. I'll save it again for you guys to look at later. I really wanted to spend a bunch of time chatting after the fact. How are we going to use this in our exoplanet toolbox? Well, once Gaia finds a star for us that shows us that it's got a wobble to it. One of the reasons it's going to be wobbling is that it has a binary star with it, or a close in eclipsing binary star, or it may, that we don't see, or it may have a really large Jupiter mass planet within its orbital plane. Whatever it is, it's going to cause that star to perturb a little. Because it's perturbing, we know something's there. Something of mass is there that's causing it to wobble. And Kepler did a great job of helping us, and even K2 now is helping us, not K2 the mountain, sorry, I'm also a mountain climber. K2 is helped us, because I think that's end of life now. Really helped us get these to discover how these planets are in orbit and how they work. It really was brilliant. It really gave us kind of the secret to unlocking photometry, and then TESS just came in and did most of the heavy lifting. Actually, I have taken dozens of observations of exoplanets from particularly TOIs, test objects of interest. I have a lot of data, and it takes weeks to get through. First of all, it takes days, if not weeks or months, to locate the star. Then it takes equally amount of time to line it up to make sure that we're going to be able to actually visually monitor this star to look for the photometry on it, and to see that movement, the dip in light that you get with photometric observations. And so ground-based telescopes, they're not the best unless you have ALMA. Now I remembered it. Atacama Desert, ALMA is brilliant. It's going to be, plus we've got the GMT when that comes online, Vera Rubin when that comes online. We're going to have lots of tools that are be at our hands that we can actually go out and with the adaptive optics down here on Earth, we're going to be able to see through all the muck that we have up in our sky, and perhaps even have the opportunity to make some confirmations. That's the hard part. RV and astrometry in general. This is a really cool video that I like to use. It just it's a 57-second video. Shows us star, planet, gives us an idea of that movement. Here we go. And RV on the right, on the left, you're getting astrometry. So you can kind of see the movement of the two masses as they kind of counteract each other and interact, perturbing each other in general. And you can and then you get a really good idea on the RV side what to look for. These are the signatures that I look for when I'm using RV data. For the most part, because of a lot of the observations that I do are down here on Earth, I'm mostly looking at astrometry. Astrometry is a brilliant tool for us. We should all be using it. And there we are. That's the end of that. Again, to the point, knowing where all these stars are, having the data on their next movements, where they're heading, within milliseconds, right? We're talking about milliseconds of accuracy. Even smaller levels. We're talking into even micrometer size. It's pretty impressive that we're getting the accurate data that we are from Gaia, hopefully from James Webb. Certainly we're going to get that from TESS, we already know for sure. I don't know if this is in the way down here. Oh, it is. Okay. With the measurements, the extremely accurate measurements that we get when we use parallax, that's how we're finding these stars. Once we have the accuracy of measurements on the stars themselves, then we can kind of bang into it and have a good look, see what's going on. And Gaia is helping us discover how these things move around. And so I'm going to go to the next slide. This is Gaia itself, how it works. I'll just go through this pretty quick. It's very stable at the moment, and because of its stability, we're able to get a really great field of view, accurate again to the milliseconds. And if anybody's done any work on Gaia before or understands it, that this is a lot of this data, by the way, was provided by Gaia to us at the Exoplanet workshop. And I think a few here, I thought I saw a few people that might have been in the Exoplanet workshop, the Sagan Exoplanet workshop with me, either online or even there. Anyway, what's brilliant about Gaia, this data particularly, is because we're getting the accuracy of the precession, that's the spin axis right here, because we're getting that accuracy, we really have, we're spot on to accurate. It's brilliant that we're able to be this fine with our measurements. It does all sky measurements. Again, you know, here's a great example of what we're getting in terms of data. So here's astrometric, photometry, spectroscopic, radial velocity, time series. Those are all right here. And then again, we're getting these Hertzsprung-Russell diagrams that are, I don't know, it's almost like the Holy Grail, to be honest with you. I don't want to get into the religious part of this, but it's feeling religious sometimes. And here we are. So this is the DR3 data. And this is telling us where to look for exoplanets. So there's so many stars, there's so many places that we can look. We have so many tools at our hand. This kind of gives us the roadmap, right? So if you need a map to get from anywhere, here it is right here. So the reason I like white dwarfs, not a lot of light, but enough light so that we don't get the overwhelming brightness of the star that kind of washes out any potential planet that might be in its orbit. And that's the reason why I like these white dwarfs down here. I really like to look down in this lower right-hand quadrant for exoplanets. I also kind of like to go down into this lower main sequence part down in this quadrant, down the lower right. If you get up into the giants, the red giants, again, not a ton of light. The surface temperatures have dropped, so we're not getting that brightness. And you're going to find some things. So again, roadmap. Where do we look for these exoplanets? Here you are. This is telling you where to look. I'm not saying not to look to the bluer side of things, but bluer, brighter, more light, much more difficult to find and see perturbations in the lights themselves, in the light curves. Light curves, everybody knows, I'm sure. This data, this was spectacular. This just came out too. Most of us, okay, here we go. There's so much data. We really have to get smart about how we manage our data. If you're going to do exoplanet hunting on your computer, you better have at your fingerprints, it better be one of the strongest computers that you can get. Highest RAM, highest number of terabyte of storage, and you better have some really good processing speed for your computer and your monitor, excuse me. And there's a reason for that. It's so much data. So this is also a great little video. This was an AI that was created. I think I have it covered up down here. Oh no, it's not here. It was created by Gaia. It's actually on their website. You can pull this data up. It's eye-opening, and I'm gonna play it now. So calibration is really important, right? And calibrating what we're seeing versus what we're reading. The data versus what we're seeing visually. This helps us understand that in the wavelengths that we're working, you can kind of get an idea down here at the bottom, the wavelengths and the nanometer wavelengths too. You can get a really good perception of, we're fairly close. Like you can kind of see they're matching a bit. They're not matching perfectly, but this is an external calibration with our fancy computers, and then this is what we get through Gaia. I just think this is brilliant. You can kind of see the stars themselves and how we're moving through the main sequence, and then up into the giant phase, and you can kind of get a look at the wavelengths. Anyway, and I think it loops. Oh, it loops back down into the white dwarfs. Yeah. Okay. Continuing on. Not the clearest image, but this was the first exoplanet host star that was located with Gaia data. And you can kind of see the number of measurements. All these black dots are the number of measurements that they made. These lines, this goes back to the days of Kepler, like not Kepler, the space telescope, Johannes. And so getting back into the days of Johannes, you take your measurements and then you just do a straight line for the next movement. And so you can kind of get a really good feel for, as the Gaia, we're looking at the data and then we're getting a good look at how things were moving around. All of a sudden, we've got a star, and then we've got something moving around the star. And you can kind of see it's fairly eccentric. Eccentricity certainly is indicative of a planet, because hardly any planet that we know of goes around a host star in an exact circle. So that was kind of eye-opening for us. HD 81040, you can look it up. Brilliant. It was their first one. And as everyone knows, right, a star's traveling through, and on its path, and you can kind of get an idea again on these paths up here at the top and around. That first image I showed you early on. Excuse me. As it moves and something is in orbit around that star, it gets this tiny little perturbation right here, and then there's another one here. So these are all individual Gaia measurements of HD 81040 as the star is moving that direction, and then boom, there's your little kick, that kick in the radial velocity. And then you go down and you start doing astrometric readings of it. And here again, these gaps tell you, something's going, something's there. And here we are. This is a brilliant example of parallax with proper motion, and then multiple measurements using astrometric data. Kind of bringing it down to kind of a closer, nearer in image. Again, in the milli-arc-second range. That's the beauty of James Webb Space Telescope and Gaia, is we're going to be at this milli-arc-second level of accuracy. And we have so much data, it's going to take thousands of us to do this. So don't fret. There's be plenty of work ahead of us for decades. It's probably going to take, each one of these takes weeks sometimes to confirm, sometimes even more. In fact, it's taken me longer. Determining the position, the parallax, the proper motion, repeated measurements. That's the beauty of Gaia. The fantastic thing that James Webb brought to us was that once we have the confirmation through our Gaia data, even the people at James Webb Space Telescope, at JWST, have told us they will practically stop what they're doing once they move through their next scientific missions, they will stop what they're doing and they will go out. And once we have a proper confirmation, they will look at our star, and they will find, particularly if it's in kind of that close parallax range, they don't want to look out too far. But if we can get into that 100 parsec range, I think they'll stop what they're doing for us. And by the way, the reason they do that is they only book out about 70% of the time on the web, and then we've got that percentage for us is available for these kind of fantastic finds that we plan on having with the repeated observations of Gaia. Summary of methods. I hope most of us know what's going on here with light curves. These are schematics of once the star comes in and back behind in the secondary eclipse, we get that weird little bump in the light as well. And you kind of see here's the orbital motion, there's the schematic, there's the light curve. Radio velocity was probably it was the first means of finding an exoplanet, and that was donkeys years ago. I think that was in 1996, I think. This is kind of the Gaia using astrometric data, and you can kind of get that little. So here we got a little notice. Sorry, solar storm warning. That's just solar wind. You can kind of see that bump there. There's another bump in its proper motion, and this just tells us there's something there. Now it's time to look for it. If we can get something that is on our plane or in our viewing plane, then we can get a great light curve, brilliant, which is why we have almost 5,000 confirmations using the light curve means of discovery, which is brilliant. This is also Dr. Perryman. If you ever get a chance to visit with him, he's brilliant. So this is kind of the meat and potatoes of why we're here today. How did we get here? What these things we don't understand. We have some idea. In my opinion, we got here because of what happened as our planet was forming, and whatever chemicals that were in our interstellar medium at their really small percentages, right? We know that the chemicals in themselves were minuscule in terms of percentages, but clearly it was something that enabled us to be here today and to have these chats. What happened 2.4 billion years ago? Well, we had an oxygenation event. We found evidence of that in Australia, up in the upper northwest of Australia, which I forget the name of the mine. It was an iron ore mine where they found this evidence. And so when you start looking at these timescales and you start stretching them out on this, it gives you a really good understanding of we're not here very long. And it's a bit humbling, in my opinion. One of the reasons why I'm so fascinated with all of this is that I have 4 children. I'm nearing 60 years old, and I thought, wow, we've got our work ahead of us. If we want to understand who and where we are in this universe, we've got to get started now. And so every day I spend most of the day, other than minding my family and my house and the kids, I think about who we are, how we got here. I have algae, microalgae, blue-green algae. Also, I think, which I have growing back here. I think there's something to the oxygenation event, and I'm looking for those fossils in some of those missions that I'm on up in the Canadian Arctic, and I'm convinced that here we are, right? We're kind of in this. Well, how do we get from gas giant to dust and all in between? It just there's a lot to be determined, and here's our kind of unknown area. How do those planetesimals? How do they accrete? And how do we get past the 1 meter problem? I don't know if anybody knows what that is, but once everything starts banging into each other in an interstellar medium, all of a sudden it's got to start sticking together, like Dimorphos, right? That was a brilliant image as we were crashing into Dimorphos. Was last week before? We were getting ready to crash into it. It looks just like a rubble pile. How does that turn into a planet? How does that turn into an iron core of a planet? Yeah, we can talk about that. Here's what Webb is going to bring us in NIRCam. MIRI and NIRCam are going to bring us some really important data. This is WASP 39b. A lot of you may have heard me. If you follow me on LinkedIn, I went nuts when I saw this. I was like, wow, this is eye-opening, right? We've got clear evidence of CO2 on another planet, and I went nuts when I saw this. I went, wow, first of all, CO2 doesn't necessarily mean that there's life, but it certainly leans towards the evidence of life. And I'm gonna take the leaning towards evidence of life side of that. And lastly, this was the first James Webb imaged exoplanet. I'm sure many of you saw this. Credit goes to the USC. USC has a partnership with the with NIRCam, and that's the reason why they get their name on this data. Yeah, that's pretty impressive. I want to go back to that. So this is HIP 65426b, and you can see the so the planet. I have a hard time discerning it, but I trust my friends at James Webb. And by the way, I have a dear friend who just left, Carl Starr, and he started working with another company, satellite company. But these are the different wavelengths, right? 300 milliarc seconds, and then and you get down to 1550, or excuse me, up to. And so you can kind of get an idea of there's something clearly in orbit around this star, and you can even get a really good idea of the protoplanetary disk here. And you can kind of see these tracks where something has cleared the tracks out. And then they think that there's a planet there. I'm going to trust them. So this is the Gaia mission archive data. You can go in and find all of this. This was that weird, that Hertzsprung-Russell diagram on page 14. You'll get a look at it. And I want to thank Anthony Brown. He really counseled me on how to present this data. I've presented this at my university, and now I'm presenting it to you folks. So here you are. I am done. Cool. Open it up. Let's chat.
That was indeed a wonderful session, Terry. It was really informative and really helpful. And that also gave a really nice glimpse for the aspiring researchers as well.
Yeah, I think we collectively as humans on this planet, with the knowledge that we have now, it is our responsibility to take and run with this. So we have within our hands the technology to do all of this work. We have the computer power. Now, ISRO probably has some really good, powerful computers. So if you can get on one of those, I would use it. Because I know that they have the good stuff. Is it possible to watch exoplanets using tech? No.
Right. Any questions?
Here's the questions. They're coming. Let's go. Yeah, that's a good question.
Yeah.
Can't really watch them. You can monitor the exoplanet. You can kind of see the dip in the light curve. So I have light curves that show ingress into and then egress out of, and I know that it's moving across that field of vision, but that's the only thing I can see. I can't see anything else. We were lucky to see that James Webb image that I shared at the last, we were lucky to kind of see those trails that are forming in the protoplanetary disk, and we're, that's real time. Well, real time, however many millions of years away that might be in terms of light. There was another bunch of questions there. I haven't followed the chat line now. Let me see if I can't get it pulled up. Here we go. So just wanted to know about career aspects in the field
If
of
anyone
astrobiology.
wants to ask questions, they can even chat.
Yeah, just come
They
online.
can post it in the chat box, or they can turn on their mics and videos as well if they want.
Well, here's a question: astrobiology. So the reason I kind of morphed into astrobiology just by chance, because I started asking the questions. Right, I started saying, how did we become who we are, and where are those links to our past, and what chemicals that we see every day when we're biology, right? If you dig into the biology side of things, when I started doing that deep dive, it was a little more than 2 years ago. I haven't stopped. I've literally been astrobiology, literally since then. And so there's somebody. Yeah, come on in. Do I need to open the queue?
Good evening, sir. I had a doubt that can we know that there is a life on an exoplanet by their wavelength?
Yeah, so what chemicals can we see in the clouds that we're looking at? That's so there are some chemicals that we really think that we find, right? Phosphine, that was a great example on Venus. So you remember that? It was a couple of years ago. Boom, we found life on Venus. And yeah, there are some chemicals, and there's some chemical chains that we know, carbon chains, that have to exist before we become a human, or before we become a plant, or before we become a cyanobacteria. Cyanobacteria, the only reason I'm here today is because I became fascinated with cyanobacteria, and here I am. I guess thinking I need to open this up here. Come on in. Can you hear me now?
Yes, sir, we can hear you.
Good. So Terry, have your wonderful lecture. Please tell us how your community website blog you can find me on LinkedIn. That's mostly where I do all of my social media. I'm on Instagram occasionally. I teach a bunch of different research groups. I have several that I'm in, and I'm a lead investigator on a cyanobacteria research group that's getting funding, hopefully, in the next 2 weeks. We're looking for, and if I get the 100,000 from NASA, then I'm very happy. I think we'll be able to do quite a bit of work. Sir,
Can you explain what is the cyanobacteria?
Cyanobacteria is a blue-green algae. And particularly, it's Arthrospira platensis. Now it's called Limnospira fusiforma. So Limnospira fusiforma, or L. fusiforma, is a really thin-walled cyanobacteria. And the importance of it being thin-walled is it breaks down. And because it breaks down simply without the complex environment that you might need if it had a really thick cell wall, that means it becomes more it can be a part of its immediate surrounding relatively easily. It doesn't take much. It can decay quickly. I started using the Limnospira platensis, or Arthrospira platensis is what it was called previously, so I still go back to that regularly. So A. platensis, I started using it to feed plants, and so most of you are well aware our soils are suffering greatly, and because they're suffering greatly, there has to be a more organic means of making our soils healthy. And in my opinion, there are. and one of them is cyanobacteria. You could spread cyanobacteria out on a big, huge, dirty plain of soil that's just not doing well. And you can do that maybe over a few months to be determined. Actually, that's research that I'm working on. And I think that, boom, all of a sudden we've got really healthy soils, and then we can start growing whatever plants we want. It's amazing how healthy plants are using cyanobacteria as a feedstock, particularly aplatensis. Again, cell wall, very thin, breaks down, becomes a nutrient source for those plants, and the root caps, or the root cap itself is what we're trying to protect, right? Sorry, I'm just reading one little note here. Sorry, I have a doubt. What is the closest exoplanet on Earth which may have life? Well, we started looking at nearby exoplanets in the, I want to say in the kind of the 30 to 100 light year. So, you know, I'm going to say Proxima is probably our best bet right now. When we call life as we know it, like you and I and people with hands and fingers, probably not going to happen. And certainly it's so far away, we may not have that real data too soon. But, you know, I'm hopeful. I'm hopeful that we're going to see something. And that something could very well be a signature in the atmosphere, right? James Webb's NIRCam or MIRI sees something in the atmosphere that can help us understand the chemical composition of the clouds. And how are we going to do that? We're going to have to see that eclipse. We're going to have to see something moving in through in front of that starlight coming through that cloud. And then all of a sudden we can do the spectroscopic reading of that light. And that's how they're helping us figure that out.
And so, can you name the first satellite which find it for the first exoplanet?
Yes. Yeah, you definitely. Sorry, that was just reading another note here. Share your LinkedIn ID and email ID and Instagram links if possible. Sure. We do that now. Yeah, you know, the beauty of what we do as astrobiologists, as exoplanet hunters, is that we can go out and we literally can find all of this data. It's at our fingertips. We just have to know how to interpret it. And I think that's where that's our responsibility, right? We actually should be doing that. Where are you? I've lost you. Sorry, I'm trying to find. Here you are. I'm going to drop my LinkedIn here. Instagram, I'll have to figure that out. I don't know how to find. I really only am on LinkedIn, and that's it. Instagram occasionally, just because I was in Paris presenting some work I did on. I'm really keen on magnetodynamics, particularly, and the reason I'm keen on magnetodynamics particularly is that our magnetic field has been in existence for 2-point-something billion years, and it's protected us as organisms, because we are organisms. It's protected us from our solar winds, our solar storms, our flares that we know are there every day. In fact, if anybody's following the solar dynamics recently, SDO is showing us that we're under the gun, literally, and it's been phenomenal to watch how active our sun is right now. I hope that, you know, exoplanet hunting in general is important because it helps us understand how other planets have formed, and that's really where I feel like that we're, you know, that missing link. What was it that what perturbation happened in the protoplanetary disk? What chemicals were in that protoplanetary disk? Well, hopefully we find those. I'm going to read Void Rex. If a planet has...
Okay, sorry.
Sorry, go ahead, Anusha.
Yes, sir. Can you name the year in which we find the first exoplanet?
Oh, yeah, I believe that was our radio velocity, 1996. Well, it was actually before that, but nobody actually laid claim to it because they had the data and they weren't sure what they had. That was our first exoplanet, I believe. I think it might have been Proxima, one of the Proxima system. Let's see, if a planet has the same atmosphere and located in a Goldilocks zone, if their life exists, it does it. Yes. Yes. No, we don't know, right? We don't know. So again, this goes back to all of the chemicals that are located in an interstellar medium that become a part of that protoplanetary disk. They vary, and you know that when we look at that, when we look at the spectroscopic data of the ISM, and we start looking at the chemical composition, wow, there is a secret. There is a secret mix. It's just like when you go out and make dinner, right? And you've got to have all the different spices, and they all have to be lined up in the right amounts, right? Just to be just right. And so that's kind of where we're at, right? We're trying to understand when we look at the ISM, when we look at a protoplanetary disk as it's forming, what are the chemicals that are coming together that are giving us that kind of that fingerprint of what might be life in general? And so that's, in my opinion, that's where we're at. We're not there yet, but we're close. The planet, what is this? How big does the star have to be for a planet to orbit around it? That's all different sizes. There's, you don't want to be too close into a super hot blue star, right? You're just going to be a rock. So you won't have an atmosphere. But if you're, several AU away from a really bright star, several AU. So 1 AU is what, 160 million kilometer, 190 million, whatever the number is. You need to be multiple AU away from a super blue hot. And if you get down, remember in the Hertzsprung-Russell diagram, if you're down in that lower right-hand quadrant, just where we are, and maybe even just below, you can be close in to that star because it's not super bright and it's not too hot. And so that helps us define what that Goldilocks zone is. Oddly enough, Earth is on the cusp of not being in the Goldilocks zone. People probably don't think about that, but we're kind of on the cusp of not being in the right spot. So that also gives us an indication of where we should be looking, and what suns and what stars we should be kind of deciphering. Let's see.
So, and can you name the satellite which founded the first exoplanet?
It wasn't a satellite. It was a radio velocity measurement from an Earth-based telescope, and I can't tell you which one it was. I'm sure I can find it, but I couldn't tell you. Can you tell something about a Starshot? Yes. Excuse me. So Starshot is interesting, right? That's SETI. SETI has some brilliant ideas. I believe that's Yuri. Forget Yuri's last name. He's given SETI. So I am a member of SETI. He's given us lots of money, and with that money, we've come up with this idea of Project Starshot, sending microsatellites on solar sails to these stars. It's going to take, if we're flying around on solar winds, it's going to take a while. But if we could get them to speed up consistently and regularly on those solar winds, then we might be able to get there within 3-4 years. They're our closest star. I doubt it. I think we're looking at 50 to more years. So in your lifetimes, but certainly not in mine, unless they have some weird chemical they can give us that makes us live longer. Yeah, Starshot, that's a cool one. Solar sails, mini microsatellites. They literally, I even have one here. This is a 1.5 U. They'll be half of this. The microsatellites, they'll be so 3/4 U, and they'll just put a little solar sail on it and send it on with cameras. Hopefully a near cam. That would be cool. Scientists always look for carbon.
What is the first exoplanet which is founded by us?
Say that again.
What is the first exoplanet which is founded by the astronomers?
What was the first exoplanet found by astronomers? Was that your question?
What is an sir? Oh, actually, the astronomers will find the exoplanets. What is the first exoplanet which is ever found it?
We found one through radial velocity in 1996. That was an exoplanet confirmed.
Yes, sir. What is the planet name? Can you say us?
No idea. Not important to me. No, now history is important, it's relevant, but what's important now is what's in front of us. We have tens of thousands of exoplanets we should be looking at. And I don't think we should be looking at the first one we found, the radial velocity, anymore. I think we need to be looking at our nearby neighbors, 100 light years or less. I think we should be looking at that. If you want to go out and find that, it's research, boom, go. Google, brilliant. I love Google. Actually, I'm not a huge fan of Google, but we're using Google Meet today.
Good evening, sir. Can I ask a question?
Oh, of course.
Sir, recently James Webb Telescope detected the artificial light on Proxima Centauri B. So it means that there is civilized person living on this stars, any planet or not, sir?
Well, you're talking about the Webb when it looked at Proxima?
Proxima Centauri B. Recently, artificial lights detected by James Webb Telescope, sir.
Yeah,
So,
I don't understand the question. I guess to me, if you're asking me about the light that's coming from Proxima, I don't know. Did it say that it was artificial? That's news to me. Now, I think it did see some refraction through the atmosphere of Proxima, but I don't think they're calling it artificial, right?
so my question is that James Webb Telescope detected the artificial light on the Proxima Centauri B star.
Yeah.
So it means that there's a civilized person live in Proxima Centauri B. Any
Yeah.
planet?
I haven't heard that, and I met with Carl Starr. I was with Carl, who was the mission operations manager with James Webb. He seeing artificial light on Proxima B. So that's news to me. I don't. First of all, I don't know that we can decipher if it's artificial light. I mean, we might be able to get some idea on the nanometer, the length of the light wave, but it's going to be hard to, at Proxima's distance, which is what, 4 light year. It's going to be really impossible at the moment. I think that's an interesting concept, though. So if there is life, intelligent life, meaning that they're able and capable of reaching out to us, touching us, not touching us physically, but touching us with their super sensitive instruments, wouldn't they have already done that? Well, probably, but maybe they haven't because we don't have the super sensitive capacity at that level to discover they're looking at us or they're listening to us. So it's kind of this competing interest, right? Well, we have better instruments than you, so we can see you and you can't see us. Sounds a lot like where we are in our world right now. Carl didn't mention anything about that, and I'd be happy to ask him for you, but that's news to me. That might be fake news. That was a popular thing here in America recently. Sorry, I was going to answer this other question about carbon life forms. I wonder why scientists always look for carbon-based life form. Yeah, silicon, nitrogen, super important. The reason we look at carbon is the carbon chain. Carbon chain enables. It's the connectivity in the carbon chain that allows other chemicals to connect to the carbon chain, and that's the reason why we look for carbon. Cyanobacteria is a brilliant example of that. As it was decaying, and it's really interesting. So the crystals that form here on Earth in gravity, and the crystals that form here in gravity, in kind of those extreme environments that when life might have formed or started to form 2.4 billion years ago, using oxygen, that decay of that crystalline structure enabled the connectivity to the carbon chain, and so that's how that's why we look for carbon. Maybe we're going to run into the wrong kind of carbon, right? Maybe we're going to run into too much CO2 as a good example in WASP. That WASP data was eye-opening to me. That meant to me that there was a real possibility that there could be some kind of life there, in my opinion. And it could just be the decay, right, of life, whatever it might be that's there. Could just be methane breaking down. Can you send your email ID if anyone has any questions for future needs? Yeah, email. Here it is. Anybody else?
So can you share your Instagram ID?
I don't remember what my Instagram is. I think I do, actually. Hang on. Let me find it. Okay, it is. There you are. I'm going to open up that link, Lois, see what we have here. Oh my God, look at that image. Wow.
Yeah, we're about to it's time, and I guess we will take last 2 to 3 questions from the audience, because we're already running short time. Yeah. So Andrew was asking how to get access to Gaia's data.
Yeah. Let me find the link for you. I'm going to just grab it, put it in the chat here for you. There you are. Be sure to register. When you register with Gaia, you get better data, and they'll know who you are, so that you're a collaborator. Then you literally become a co-collaborator once you register with them. Anything else, team? Happy to chat about anything. Coffee. Where did coffee come from? Do you ever wonder? And then where did flowers come from? Anyway, I could go on about all the cool things that we have.
Yeah, but cinnamon was definitely imported from India.
Yeah, totally.
And it's the least, important ingredient that we actually use in Indian kitchens. We don't use that much.
Yeah, our world is, I feel, this is why I think I get up every day and do what I do, is that I feel like our world is at a tipping point. So I'm worried about our ocean currents. I'm working on and with ESA on a project to kind of chart and map more precisely what's going on with the Gulf Stream. The Gulf Stream is scary because of its change in speed and its temperature change. It's slowing down, and because it's slowing down, it's allowing for those perturbations up in the Canadian Arctic and to happen, and so you're getting those weird drops in the polar vortex. There's some worrisome things going on. Why we look at exoplanets. Well, this is a great example of how they formed, why they formed the way they did, where they did, particularly where they did. And, maybe we'll find something one day that gives us that little secret, just to kind of help us, because we're certainly not omnipotent and all-knowing here on planet Earth. We definitely are behind the curve, in my opinion. And we have our work cut out for us as scientists. And we should be focusing on these types of things every day. And we should get up every morning and think, what is it I can do today to help save this planet? And that's a lot of pressure, but we should all be thinking about that. And that's almost our responsibility, and morally even in some respects, because we have that knowledge. And I hope everyone takes that to heart as well. It's a lot of pressure, but let's go. Get it done.
Right. I guess we don't have any more questions. And on that note, let's end this session for today. I would like to request the audience to kindly turn on the cameras to capture this moment.
Bonnie, it's late there. You must be getting ready to hit the hay. Probably get to bed
It's
here.
9:16 p.m.
Yeah. I have close friends in Nepal, and so I'm speaking with them regularly, and they're 11 hours and 15 minutes of change. I'm like, how is it? It's 11:15. I don't understand. Anyway.
Huge difference.
If you're ever in San Francisco, call me.
Thank you. Yeah, sure. What's the time there?
I am 8:47 a.m. I got up early to hang out with you.
Early morning for you.
I like that. I like getting up early.
Yeah, right.
It's quiet, right? It's always quiet in the mornings. I like that. Gives me time to think.
Yeah. Yeah, right. That's good. Always to be an early bird.
Definitely. The best food in the morning.
All right. Thank you, everyone. And thank you so much, Terry. It was an honor to have you today. And it was a wonderful section. We got to learn so many things. And I will also personally try to implement all the methodologies that you taught us today. So much for being with us.
Awesome. I'll drop my slides on the email, and I'll send that over to you guys.
Thank you, Terry sir, and all for wonderful session.
Anytime. And if anybody needs anything, drop me a note. I can chat. I'm always around.
Thank you so much.
See you.
Thanks for
Yes,
joining
sir,
us
please
today.
give your Instagram ID.
Yeah, I threw it on there at Planetary Space. It's right there, just under it. Put it on. It says at PLANETERRY space. Jump on. I don't do too much work on Instagram, but I do a little. See y'all. I'm gonna head out. Good night. Sleep tight.
Yeah.
Don't let the bed bugs bite. That's what we say here.
Thank.
Bye. See you, Bunny.
Have a great day. Thank you so much.
See you.
Yeah.
Bye. Be safe. Take care.
Take care.